Morning to all of you. I, Dr. Nirav Bhai Pandya, warmly welcome to all of you. I, our Dr. First of all, our today's speaker totally yes, application is indulged, but system properties again. Welcome to you.
Visible? Department of Physics, Dr. Me, with a very good author delivered about things. We will tell dielectric oxides and beam irradiation material. Let's start. How can thin one thin sub on a micro base considered to be thin when its properties significantly differ from the bulk. With a small introduction of that, when it's the thin films. The use of thin films is found by gold decoration. But when did it all went along with thin film? The first deposit chemistry, iron oxide. He deposited iron college. What happened? Physical wave. Robert day of vacuum. Oxide. So the in which the of things is in film. People were much more interested in observing and interpretation of the interference pattern that is related to the thin films. Then all research and film is why you is of from 1940 to 2005, the optical application, the insulating application of thin films. So then the booming of nanocrystalline thin film materials started appearing. From 2005 till date, the thin films finds many application in most of our daily aspects, like in memory devices, sensors, photonic devices, optical fibers, and laser optics, fuel cells, and energy storage. So today we will be discussing mostly on the memory devices, especially the non-volatile memory devices. The high dielectric oxide thin films for non-volatile memory applications will be discussed within the next few slides. Why high dielectric application is high dielectric oxides are very important. In 2005, what we can see here in this figure, we can see that there is a small micro SD card which we all use, which had a the same size storage density of 128 GB. That means the same size but much more. Need much the current used one. That is, or the size of the thumb, and we need the like possible. It all started with the Moore's law. Some says it's a strict law to be followed, but others says it is basically of transistors in an IC doubles every year. So here is the conventional devices people have used for scaling performance and all, which we all faced in our mobile phones. And so one of the solutions to have size decreased and increased electric oxide layers, and also capacities which have different high dielectric oxide layers, like it has been widely studied in the industry since many decades, and Al2O3 is considered to be the short-term solution, and HFO2 is considered as a potential replacement of SiO2, and which is it is already been starting to be replacing. And gold is very easy to synthesis, and it is having high density of states. So these three materials and gold layer, what we are going to try is we are trying to make a non-volatile memory structure with gold and nanocrystals to be embedded to act as a starch storage device, and is a non-volatile memory device. For that one, we have used different physical vapor deposition techniques. And we have characterized the samples with X-ray diffraction, TEM, transmission electron microscopy, Rutherford backscattering spectroscopy, atomic force microscopy, X-ray photoelectrospectroscopy for compositional studies, and capacitance voltage to understand whether the stack structure works as a non-volatile behavior, shows a non-volatile behavior. So we are going to discuss on hafnium oxide tunneling blocking layer with gold nanocrystals embedded first. So our objective was to fabricate a tri-layer structure of hafnium oxide, gold hafnium oxide. There's a tri-layer structure, and to see whether it is having a non-volatile behavior because of gold nanocrystals. So what we have done is we deposited the material using RF magnetron sputtering, the tunneling and blocking oxides, that is the HF42. Here you can see the schematic illustration of the tri-layer structure. The top layer is the gold layer, and lower layer oxide is the tunneling layer, which allows the electrons to tunnel, or electrons or hole to tunnel through the small layer. So what we have deposited the structure, and we have characterized it. Before characterizing, we annealed the sample at 650, 750, 850 degrees Celsius in nitrogen ambience for 60 minutes. So what we got from the structure is through Xrd we got the tri-layer structure as deposited, as amorphous, and as we have annealed, we saw that the structure, the amorphous nature changed to crystalline, and it exhibited the monoclinic structure as previously reported by the literatures. And the same thing is confirmed by TEM, which we can see that there is a crystalline nature of monoclinic is shown in the SAD pattern of hafnium oxide, and we can also see the gold nanocrystal HRTEM image showing that there is a crystalline nature of gold. And we calculated the average nanocrystal density, which is around 1 × 10⁻11 as obtained. And we also did the SGEM and EDX studies, that is mapping, and we confirmed the presence of gold, hafnium, oxygen through this. Now, we have deposited films is seen to be very smooth, uniform, and high deformations. But as we can see, as we increase the annealing temperature, we can see that there is a small increase in the surface roughness. And to understand more about compositional properties, we have done the depth profiling of our sample, and we got this figure is about the blocking layer of our different samples, like as deposited 750 and 850. From this one, we can understand that the HF42 is being formed, and we can see in the as deposited case itself there is a suboxide formation, which is somewhat reported. But once we analyze the samples, we can see that the suboxide increases, and also there is some at higher annealing temperature there is the presence of hafnium metal. In the case of gold charge trapping layer, what we understood from the depth profiling or through XPS is that previous literatures, we can see the main peaks of 83 and 86 of for F5/2 and for F7/2 as expected. But once we increase the temperature, which we anneal the temperature, we can see that there is a small slight shifting of binding energy towards the higher binding energy, and this is reported. This is at crystals. And through XPS also we can see, or we can confirm the formation of nanocrystals directly. In the case of hafnium oxide, we have seen that there is the formation of hafnium silicates and silicates. Also, the XPS was also confirmed. The results were confirmed through RBS, which shows the presence of hafnium, oxygen, and gold. And it also shows there is an interdiffusion, just like in the case of hafnium oxide tunneling and blocking layers, which we have expected. Here also we are seeing, and the total thickness is estimated around 37 nanometer. And the non-volatile memory characteristics was confirmed through CV, capacitor voltage characteristics. Here we can see the reference sample, that is without the gold layer, that is only hafnium oxide layer on silicon, and the gate oxide is with the electrical characterization, and we can see the charge effect mainly comes due to the gold, because here we can see there is a charging and hole charging. That is, when a positive gate voltage is applied, the electrons from the silicon substrates will be injected into the nanoparticles. And since it is the electron injecting, we can say that it is the electron charging which happens here. And when we apply a reverse voltage, the reverse will happen. That is, the electrons will jump from the nanoparticles, or we can say that the holes will be jumping to the gold nanocrystals. So there will be a hole charging, and we can say that there is a discharging process that is happening, and there is a definite CV hysteresis because of gold layer. And this is where we are confirming that there is a non-volatile memory behavior of our deposited filaments. So this study demonstrates the structural, morphological, and electrical properties of HFO2 gold HFO2 layers. And it also shows that the gold nanocrystals is having a charge storage behavior for non-volatile memory structures. And now let's discuss the previously we have already mentioned that we have used 3 layers, that is HFO2, SiO2, and Al2O3. We made tri-layer structures with that one. And first we have already discussed the tri-layer layer, strapping layer, about tri-layer structure. Previously, we have also deposited the silicon dioxide layer with the sputtering process, that is RF Mgtr sputtering, and we deposited the gold charge layer, charge trapping layer using the electron beam evaporation system, and we annealed the samples at 650, 750, 850 in nitrogen ambience for 60 minutes. The Xrd of this structure gave some exciting results, like the whole structure is amorphous in nature as it was expected, and also at high temperature 650, 750, 850 degrees Celsius, the amorphous behavior continued. Same thing which we have seen in TEM. And to see the nanocrystal formations, we have done the TEM, and we saw the gold nanocrystal formation, and we calculated the average nanocrystal density around 1 into 10 raised to 11 centimeter square. And the same thing we have seen, we confirmed the presence of gold, silicon, and oxygen through EDX mapping and STM images of gold. And we have so that as previously we can see the absence of any visible pores, cracks, voids is visible in the figures which is shown here, and it shows that RF Mgtr sputtering is a good technique for the deposition of oxide materials, as previously reported by many researchers. And we can see the peak to valley surface roughness decreases with the annealing. Understand the surface morphology, the compositional property, we have done the XPS studies, just like the previous we discussed about the hafnium oxide layers. The blocking layer is shown here, the as deposited film, the blocking layer, the charge storage layer, the tunneling layer. It shows that the silicon dioxide formation, and it also shows the gold with gold oxide. Once we discussed silicon dioxide formation for the charge trapping layer. So once we are seeing this one at 750, we can see the gold spectra is having two peaks. But at higher annealing temperature, we can see that peak shifts towards higher binding energy, as we have discussed previously in the case of hafnium oxide structure, which shows that there is a formation of gold nanocrystals. So we are going to see the RBS, the results. The RBS results also confirm the formation of SiO2 gold layer, and also it shows the interdiffusion, just like this tunneling layer, that there is a small formation of SiO2, SiO with the SiO2. So in the simulation, small total thickness was also estimated to be around 38 nanometers. In the case of CV, we can see the hysteresis loop is as expected, that the hysteresis loop indicates the charge storage capability of gold nanocrystals, that the SiO2 gold SiO2 structure behaves as a non-volatile memory, and it is also having an electron charging and hole charging, just like in the previous case which we have discussed with HFO2 structure. So in the summary, we can say about the SiO2 gold SiO2 structure is that we were able to successfully fabricate a tri-layer structure, and we understood that the crystal in charge storage behavior at high temperature and less. In the case of Al2O3 gold Al2O3 formation, here we have deposited the Al2O3 layer. Instead of hafnium oxide and silicon dioxide, we are using the another oxide, high dielectric oxide, which is aluminum oxide. And we have deposited the aluminum oxide just like the previous thing, like the sputtering, the technique. And what we have done is we, just like the previous structures, we have annealed at the samples at 650, 750, 850 in nitrogen atmosphere. And the results of HFO2, the Al2O3 is very quite understandable, that the Xrd patterns shows the as deposited amorphous nature, and it is also seen to be various literature reviews by various researchers. And in the case of TEM, we can see the gold nanocrystal formation, and the density of nanocrystals was calculated around 2.16. Sorry, much case and SiO2. In the XPS case, in the XPS analysis, we got the Al2O3 formation, and also we got gold oxide as also gold as deposited films. But in the case of high annealing, we also got a slight shift of 0.3 towards high binding energy, which showed that the gold nanocrystal is being formed. And in this case, which is very interesting, is that one. In the case of tunneling layers in the three, which we can see at as deposited at 750 and 850, in the tunneling layer, we can see there is no formation of intermediate oxides like SiO and also hafnium suboxides. There is no formation of suboxides in this case. So what happened here is we were able to deposit in to understand more about the compositional properties, we did the Rutherford backscattering spectroscopy, and we understood the presence of oxygen, aluminum, and gold, because we fitted the peak using a RUM simulation. and the total thickness is calculated around 37 nanometer. And to understand the non-volatile behavior of the tri-layer structure, we did this current, the capacitance voltage measurements. The center of hysteresis curve comes around 1 volt, and we can see the electron charging and hole charging, and the memory window is obtained around 3.9, which is much more higher than the previous SiO2 and Al2 SiO2 and hafnium oxide case. And the hysteresis curve confirms a significant role of gold nanocrystals for non-volatile memory behavior. So here in the case of the summary, to sum up, we can see the non-volatile structure with Al2O3 channeling blocking layer with gold nanocrystals embedded have been fabricated on silicon substrate, and the results indicates that there is a non-volatile memory behavior of gold nanocrystals, and it is confirmed through capacitance voltage measurements. And also XPS shows also confirms the formation of gold nanocrystals. What we understood from the study of hafnium oxide, gold hafnium oxide, SiO2 gold SiO2, or Al2O3 gold Al2O3, is that among various gold nanocrystal based memory structures, we understood that the tri-layer structure with aluminum oxide shows promising memory effects than hafnium oxide gold hafnium oxide and SiO2 gold SiO2. The reasons for this increase in memory behavior in Al2O3 gold Al2O3 is because, as it is shown in Xrd, it is amorphous, but in the case of hafnium oxide, it was crystalline. So the crystalline structure led to leakage path, and as a result, the charges which is stored is leaked through this leakage path, and the Al2O3 is higher, having higher dielectric constant compared to SiO2. This is another reason. And in the case of Al2O3, we have not seen any interfacial layer formation, just like which is been seen in hafnium oxide and SiO2 tunneling layer at high temperature, which is previously discussed with XPS. And also another reason can be the density of gold nanocrystals in the form in Al2O3 matrix. Now the second topic is in and around ion beam irradiation of high dielectric oxides. So what is an ion beam? Ion beam is a beam having particles, basically positive ions, with high energy, and its energy varies from few keVs to few hundred MeVs. So an ion beam is basically classified into two types: low energy ion beams and high energy ion beams. As the name indicates, the low energy ion beams are having energy lesser than 100 keV, and the higher energy ion beams are ion beams that are keVs to MeVs. Now, what is shift heavy ion? A shift heavy ion beam are heavy ion beams that are having high energy in the order of MeVs. And what are the uses of this high shift heavy ion beams or ion beams? The ion beams are mainly used for material synthesis, material modification, and material characterization. Here in our talk, we are going to discuss about mostly around the tuning of magnesium titanate using shift heavy ion beam irradiation. Why magnesium titanate is important? For microwave integrated circuits, microwave ICs, it requires thin film material with high dielectric constants, and it must also have low dielectric loss and good stability. That's why we choose Mgtr3. Since Mgtr3 is having dielectric constant of 17, and it is having a low dielectric loss because of its quantum structure, that is AbO3 structure, and it is having very good thermal stability. What we have done here is we have prepared the target, the sputtering target, using mechanochemical methods. That is, we took MgO and TO2. It and we at high temperature, and we made TO3 were deposited with this targets, and this target is with high stoichiometry. Eventually, the two sets of thin films which we deposited, that is with a different oxygen mixing percentage, we irradiated it with 100 MeV gold at a fixed fluence of 2 × 10⁻13 ions per centimeter cube. So what we did here is we just deposited the film with a different oxygen mixing percentage. Then we annealed the films, and these annealed films gave very good crystalline nature. And with this crystallinity, we irradiated the films with 100 fluence. So in the Xrd analysis, the films exhibited polycrystalline trigonal structure after annealing, just like previously I mentioned. And we can see with the ion beam irradiation, there was a change in the crystallite size from 24 to 20 in mixing process. From 29 to 15, that is from 2x to x, that is half it reduced in the case of lesser zero oxygen mixing percentage. And this crystalline structure reduction may be due to films with higher fluence that resulted in multiple ion impacts, and hence there is a small broadening of peaks as we can see in the Xrd pattern. And this shows that there is a SHI, that is shift heavy ion irradiation induced. There is a small SHI induced partial amorphization. So in the case of morphological properties of Mgtr3 films, we can see at high without irradiation. Before radiation, the RMS surface roughness, was around 6 nanometer, and after irradiation, it drastically reduced to around 3. And this decrease, we can see in the case of two scales, similar report of decrease in the nanometer surface roughness. The decrease in roughness indicates that the surface is smoothened by the rearrangement of atom, by electronic excitation and ionization because of the effect of shift heavy ion. In the case of optical analysis of Mgtr3 thin films, we have seen that the band gap decreased with the irradiation. That means in the previous as deposited case, it was 4.7 and 4.1, but in the irradiated case, it decreased up to 3.2 and 3.5. The transmission fringes here, we can see that there is some transmission fringes, and this is mainly due to the substrate film interface. And also we can see that this decrease in band gap or decrease in the properties is can be attributed to the appearance of defect levels. So what we understood from this Xrd, AFM, and optical analysis is that the shift heavy ion is one of the best and reliable techniques to tune and modify, since the structure and optical properties of Mgtr thin films, because we were able, the Xrd results shows a drastic decrease in the crystallite size, and also there is a change in band gap. So to conclude, the non-volatile memory application of high dielectric oxides with HFO2, SiO2, and Al2O3 in gold has been discussed, and shift heavy ion beam irradiation on high dielectric oxide films of Mgtr3 has been discussed. These are the acknowledgements. Thank you. And we are open to any questions. Yes, it is over. And we are open to questions.
Thank you very much, sir. Very informative session. Participants which are here. Anyone would like to ask any question? Okay. Question. So to execute, and
yes, sir.
Thanks to today's speaker, Dr. Arun Vinod sir, first of all accepting our invitation, okay, and for providing very informative webinar for all of us. Thank you so much, sir. And we would also like to thank all the participants which are available here, as well as those who are available on the Facebook and Google Meet.
Sir, wait a minute.
1 minute, sir. I want to ask some questions.
Yes, sir. Would you like to ask anything, please?
Yes, I want to ask you questions. Yes, sir. Just to say me, how can you calculate the fluence?
Hello?
How can you calculate the fluence for the shift heavy ion?
Sir, there is hello.
Yes, how can you calculate the fluence?
Sir,
What is
there is with that equation we use the energy and all, we calculate the fuel lines.
And the memory, high dielectric, and the non-volatile memory applications. What is the importance of it?
In the conventional non-volatile memory, where we are using silicon dioxide, the scaling down is having a big problem. We know that once the scaling down of devices happens, in the case which we all have faced, scaling in our mobile phones and all, what we can see is the device is getting much more rapidly heated, and also
Yes.
once we are opening the apps and all, it is getting stuck. So this is one of the basic problems which we are facing. And to have the solution, just like I previously showed in my slides,
Yes, just can you
is it visible?
no, it's a problem.
Yeah, it is visible, right? So in the case of high dielectric oxide, it is potentially expected to be alternate replacement of SiO2, because it gives much more capacitance, and also it reduces the heat dielectric. That means it is 60% greater in efficiency or in capacitance, and 100% reduction of dielectric leakage. And as a result, we can see that there is much more faster communication, and the device will be much more cooler. So this is the use of high dielectric oxides in the present scenario.
Okay. Can you again just to tell me? Not stop here. Yes, you are using the gold.
Yes, sir.
Yes. And what is the importance of gold nanoparticles here? You can use the silver
Ah,
also. You can also copper also is there. Platinum is also there.
sir, the use of gold is because it is having high density of state when compared to copper, and it is fundamental well, so that there will be a definite trapping of the charge. And when we see the chemical stability, say in copper and all, chemical stability is one of the biggest concerns with the metal nanocrystals. But in the case of gold nanocrystal, chemical stability is much more reliable. And the case of gold nanocrystal, it is very having very ease of synthesis, and the work function of gold is very much to the working of the device structures. This is why we use the gold nanocrystals.
Can you show me the one RBS from the SiO2, AU, SiO2?
Yes, sir, sure. Yes. Hello.
Yes, yes. Hello.
Yes, sir.
Uh, Here you can use the calculate the thickness of 38 nanometer. How can you calculate?
Sir, we have used a standard program called as a rump simulation program, and with respect to this rump simulation program, we have calculated the total thickness to be around 38 nanometer.
In this case, if you want to calculate the RAM, but in a gold is in between the SiO2, AU, SiO2. Okay,
Yes,
then
sir.
the
Yes, that's why we used the total thickness.
okay, total thickness. But can we
Yeah,
calculate
we
the
have
separate thickness of that? Can we calculate the separate thickness of gold in this one?
it would be mostly very much difficult, but as I can understand, that will be very much difficult to calculate the separate thickness of code.
Any other software is there? Calculation of the thickness
Yes,
and
sir.
the RBS separation. Any other software is available for that
Yes,
calculation of RBS?
yes, sir. There are other softwares which are available, and I also tried with the Simnara, which is another software which is an alternative to RUM simulation, which is very easy and very difficult in the meantime.
In AL203, which is the best? AL203, SL2, HF4.
In the case of the samples, we have seen that the L203 gold L203 structure is much more better
Okay.
when compared to the other two structures. It is because the L203 is having a very good memory window of around 4 volt, which is much more better than HFO2 structure and SiO2 structure, which were all around 1 or 1.2. So, and it also shows the density of gold nanocrystal much
This is this thickness.
the tunneling layer thickness allows the electrons or holes to tunnel through this layer and to be stored in this charge trapping layer. And the thickness of blocking oxide, which prevents the tunneling, the back tunneling of the charges to the gate, and it provides a very good insulation. So both of them are very important, and it's proved to be very steady.
Questions. Which substrate? Sapphire substrate is also available. Quartz is also available. Which is the better for memory window?
Sir,
substrate
for
is
memory window, it is we all use silicon because that is very important.
why we use
Because
silicon?
that's where we need much more the band gap alignments and all.
Thank you.
Any question, Mahendra sir?
Yes, sir.
Yes,
Shardul
Sadhu sir,
Vadalkar
would you
here.
like to ask anything?
Yes, sir. Shardul Vadalkar here from
Yes.
physics department. And sir, I have observed that the thin film is a very popular subject in experimental physics. Could you explain me why?
Yes, Mr. Sradul, I'm
Shardul. Yes, sir.
pronouncing it correct.
Shardul.
Ah,
Shardul
Shradul.
Vadalkar.
Shradul, you asked a very good question about thin films. So let's see why the thin film is very important. Just like you asked. I'm just going to show you a video. You can see this one.
Yes, sir.
So directly or indirectly, in the most things which we use nowadays, it is all with thin films. Just like you, if you take your spectacles, your eye neck, directly what is happening there? There you can see a small layer of thin film, and we can say that that is one of the biggest applications which we daily encounter with. Also, we can see in the case of your mobiles and all, it is all having memory devices, it is all having electronic devices, and this whole components like the thin film transistors and the field effect transistors, the sensors which we use in our phones, they are all having an application, or this all being substituted with a component of thin films. In the case of antibacterial studies, we use thin film. In the case of fuel and energy storages, we use thin films. And in most of our daily life activities, we see that the thin films is directly a role in our. So these some of the applications of thin films, and even in the corona analysis and all, we are using some methods. So the thin films are very important. I hope I replied to your question.
Yes, sir. Sir, I just wanted to ask you one last question. That the
Yes, sir.
properties like surface properties like surface to volume ratio, etc., they play very important factor in this huge interest. Researchers are very much interested in thin films because of the surface properties of thin films. Is it so?
Yes, it is. It is very much. You are correct, because surface to volume ratio is very much important. Yes, you can see the gold and all. You can see when we compare with the bulk counterparts, the bulk material, the nanocrystal or thin film material shows an entirely different behavior. So in that aspect, whatever you are saying is very much correct, and that's why the thin films or the nanotechnology is been having a boom or have the highest significance with the researchers. Yes, Shardul. So happy to have a word with you.
No, sir. Okay, that's it then for today, I guess.
Is there any question, Sadhu sir?
No, sir.
Okay.
No.
Thank you, Sadhu sir. Is there any question from other participants? Okay, so I think there is no question. So thank you very much, sir, once again, and thank you for providing very informative session for all of us. Thank you so much.
And also, sir, I am so much happy that Parvati University has invited me to deliver a lecture. I'm inducted to Parvati University, and I have heard many times about Parvati University and thanking the administration and the university for giving me a chance, especially the Department of Physics, and Nirav sir, and also Mahendra Singh Rathore sir, who is one of my collaborators, and so happy to be with the Pali University. Thank you very much for inviting. Thanking again.
Thank you. Thank you so much for